At the stroke of the midnight hour, when the world sleeps, India will awake to life and freedom.
India is celebrating its 75th year of independence, which has been named as Azadi Ka Amrit Mahotsav. One of the themes in this celebration has been the contribution of scientists in India's freedom struggle. You may think that what exactly can be contribution of scientists in freedom struggle, but if we really think deeply, we find that their contribution is no way less than that of the freedom fighters who sacrificed their life for the country. The S.N. Bose Center has organized a series of talks to basically discuss the life and work of these great luminaries.
I will now show you a picture of several scientists, and these are the people who made this revolution possible. Now, when you look at this list, all eminent names, very famous names, there is one person who seems to stand out like a sore thumb, and that, of course, is in the corner here, Satyendranath Bose. But these stories should begin at the beginning, so let's start there. And I take you back to the 19th century, to Europe, and to the city, beautiful city of Munich in the 18th century. That's a picture of Munich with its famous cathedral. And I take you to this gentleman whose picture is in the center holding a prism, Joseph von Fraunhofer. He was a German optician who invented the spectroscope in 1814. More than 200 years ago. And what did he do? That when you looked at the sun through the spectroscope, you see all these black lines in the middle of the spectrum. And these lines are known as Fraunhofer lines. But if you look at the sun during an eclipse, suddenly those dark lines become bright lines. Now, nobody understood what was going on. So only half a century later came the understanding. And it came with the discovery by a gentleman called Robert Bunsen of this humble instrument called the Bunsen burner. Now, what Bunsen and his student Kirchhoff found is that when you look at the light which is coming from the Bunsen burner, from the flame with different element salts in it, you find the line spectra, which you're getting line spectra, and they match with many of the line spectra of the Fraunhofer lines. So the understanding of this came from, it was worked out by Kirchhoff. He proved using thermodynamics that the absorption spectra and the emission spectra must be the same. Okay, so the first people who actually did a detailed measurement of the black body spectrum, I'm showing you a modern graph, but there were these gentlemen, but I will show you their graph also, but Loomer and Pringsheim, and they did detailed measurements to see how the black body spectrum varies. So this is how it varies as the wavelength goes up or the frequency goes down, whichever way you want to think of it. So when this happens, you will get a rising curve and then it falls off again. So the first person to try to explain it was a gentleman called Wilhelm Wien, and he found a formula which seemed to match for small wavelengths, but which became very poor for large wavelengths. This Rayleigh-Jeans formula, it happened to do exactly the opposite. It worked well at the upper end of the spectrum. I'm trying to match this 7,000 Kelvin. It worked well at the upper end of the spectrum, but as you went to the lower side, to the small wavelengths, that is large frequencies, it just grew and grew. The answer came from Max Planck, who in 1900, he made an inspired guess or maybe a desperate guess, or we don't know how he arrived at it, but he suppose these energy values, instead of being continuous, so you do an integral, suppose you make them multiples of an energy packet. Suppose you make them integral multiples of some E naught, which is some fixed number. These are the actual data presented by Lumer and Pringsheim. And you see that the matching is almost perfect. So, if you got such matching in the laboratory, maybe your teacher will suspect you of having manipulated the data. It's such wonderful agreement. Okay, this solid line is the Planck formula. The dashed lines are the Wien formula. So it's simply too good to be a coincidence. So therefore, we have to conclude that Planck's starting point, that the energy values, instead of being continuous, there must be integral multiples of an energy packet. This must be true. So to give an analogy, you think of a tap. If you have, after all, how does water come out of the tap? It comes only as droplets. So if you turn down almost close the tap, you will get one droplet of the other. These are discrete droplets. But when a large number of them come out, then it looks like a continuous flow. So this was Planck's idea, that it's the container, it's the walls which are responsible for this, and that's why you're seeing this behavior. But alas for Planck, his own best friend, I don't have to tell you who he was, he killed the idea. How? Because within 5 years, he came up with this theory of the photoelectric effect. So the photoelectric effect, most of people know this, it shows that when you get this famous equation, but it shows that when energy is coming in, it's also absorbed as packets. So these photoelectrons which come out absorb a finite energy, h nu. So this theory shows that energy is also absorbed in packets. Now, of course, how does this fellow know, this electron know that the energy has to be made into a packet before coming? It must already be in a packet. So therefore, if energy is emitted as a packet and absorbed as a packet, then in between it must be staying as a packet. After all, before it's absorbed, who will arrange it into a packet again? It's not possible. So therefore, energy must be always remaining in these packets, which we call quanta. And the modern name for it is photon. The solution, when it came from a quite different part of the world. So this is a good point now to start and tell you about the making of SNOs. So let me take you to Kolkata, Google map of Kolkata, and this Google map again. I take you to this place, which is in the Goa Bagan area. You see Goa Bagan Park here. You see the Scottish Church College, Hidwa, in this area. And here to this road, which is called Ishwar Mill Lane. So this house in Ishwar Mill Lane is still very well preserved. And of course, the photo was taken quite some time back, which is why you see this man-drawn rickshaw. This house is where Satyendra Bose or Satyendra Bose was born at 22 Ishwar Mill Lane in the Goa Bagan area on the 1st of January 1894. In 1909, he joined the Presidency College, and then he won his MSc in 1915 in the mixed mathematics course, and these are his marks. So amazingly high marks if you know Calcutta University. But then things changed in 1919 with the Jallianwala Bagh massacre. And it is really with the Jallianwala Bagh massacre that Indians actually turned against the British Raj. Well, Bose was sympathetic to the national cause. He was always a good friend of the revolutionaries, but he did not participate in the non-cooperation movement as such. And in fact, Sir Ashutosh, who was the vice chancellor, he didn't approve of disorderly agitation. So he was sympathetic to the cause, but he also did not. But 80% of the students of Calcutta University responded enthusiastically. They boycotted the classes, they publicly made bonfires of foreign goods, brought in Swadeshi and so on. So that story, of course, we have learned, we'll read elsewhere. Now, in retaliation, the government of Bengal, they threatened to withdraw all the financial support to the university. I mean, that is how governments respond, unless the university agreed to 8 conditions, which Sir Ashutosh described as humiliating. And they would basically give the Sarkari officials complete control of the university's internal matters. So those of you of us here who are listening to this and who know anything about administration of science will know that this is a long fight. I mean, it hasn't changed after independence, it continues. But Sir Ashutosh, of course, he was known as the Tiger of Bengal. He fought this tooth and nail, but by 1924, he was dead. And he was succeeded by somebody who basically gave in to all those 8 conditions. But at that point, when the financial support was being threatened to be withdrawn, some of the jobs would then go, which were financed by them. Among the jobs was that of Bose. So in 1921, Bose found that even though he had not participated in the non-cooperation movement, he was likely to suffer for it by having his job withdrawn. Now, at this same time, Sir Philip Hartog was given the job. So he came from Oxford. He was given the job of setting up a new university at Dhaka. And, he handpicked Bose and some other bright sparks, including R.C. Majumdar, J.C. Ghosh and others, persuaded them to move to Dhaka. And Bose, because his own job was not certain, he decided that, okay, he would move to the University of Dhaka. He got a promotion then. He would be offered a reader position instead of a lecturer here. What you see here is the famous Curzon Hall of Dhaka University. This is the physics department is on this side. On the table of the sahibs are scattered lots of nickel prisms, lens and eyepieces. It would require a lot of research to determine which belongs to which apparatus. We do suffer from lack of journals and so on. They are talking about having a separate science library. Bose, who was teaching thermodynamics of black body radiation, complained that the theory of Planck was hard to teach to the students who kept asking awkward questions. So, good message to students. Please do keep asking awkward questions to your teachers. Who knows, maybe a great discovery will come out of it. Now, Meghnad Shah, who had recently moved to Allahabad University, Allahabad University was well endowed and they had a much better library. So they were getting the contemporary journals. So it was Shah who had informed Bose about these papers of Pauli and of Einstein and Ehrenfest, which had just come out. Bose had not seen them. And Shah, in the fashion of those days, he had gone to the library, he had taken those journals, and in his notebook, he had copied down notes from them. So he lent Bose those notes to look at. Now, I should let you a little bit, so that in as early as 1903, and then Fokker, Lorentz and then Fokker had shown that the momentum transfer between free electrons and radiation. So imagine that imagine that the red things are photons and the other ones are free electrons. So the momentum transfer, when you put them together in a cavity, it can't take place if you have only radiation pressure. Okay, so radiation pressure was the only known way by which momentum transfer was known to take place. He showed that if that happens, you will never get equilibrium. It's too weak. But Pauli had showed that you could do that through Compton scattering. But in order to do that, he used the formula I showed you with this nonlinear term, which violates causality. So Bose looked at those, and then, of course, I told you about the Einstein Ehrenfest calculation. So this is what they were trying to do. And Bose looked at those, and they all looked fishy to him. He thought he would treat the photons purely as a gas. For photons, now Bose made 3 crucial physics assumptions. the three major discoveries in this: uncertainty, wave particle duality, and spin. But he had not worked those out in his mind in detail, but somehow he had some amazing intuition, so he was able to put these in. And he wrote it up in a very modestly titled paper, Planck's Law and the Light Quantum Hypothesis. Towards the end of 1923, he sent his manuscript to the Philosophical Magazine. That was sort of the top journal in those days. And he sent it for publication there. So in the way which journals do, the journal sat on his thing for 6 months. And after that, they sent back his manuscript with a very curt note saying, sorry, we can't publish it. The referee's note is negative. Your paper is wrong, so we won't publish it. And he decided to send it to Einstein. So, in those days, Einstein had become the editor of this new journal called the Zeitschrift für Physik. And people who couldn't publish their papers elsewhere would send it to Einstein. He added a note of support at the end saying, in my opinion, Bose's derivation signifies an important advance. The method used here gives the quantity of ideal gas, as I will work out elsewhere. Notice he doesn't say we will work out elsewhere. I will work out elsewhere. Come back to that. He neither invited Bose to collaborate, nor did he ask Bose to visit him at Berlin. He's publishing his paper and now I will take it ahead. Okay, moreover, he changed Bose's idea. This, of course, there is no proof because the Bose's manuscript is lost. But Bose said it many times that I wrote about angular momentum and he changed it to polarization. So Einstein changed it to polarization in the translation, and that's how you got this factor of 2, okay, and the factor of 8 there. The only person who ever stood up for his spin idea, of course, he had won some recognition, was C.V. Raman. In a paper with Bhagavantam in 1931, he later wrote, we understand from personal communication by Bose that he had actually taken this plus minus H. Anyway, what happened here was that with Einstein's postcard, it helped to smooth the path to getting visas for Bose's Europe trip. So they were financed by Dhaka University, and for the German visa, because Einstein had written, his visa fee also was waived. As soon as he had got there, he wrote to Einstein. He addressed him as master. Einstein was the great Einstein. I've been granted leave by my university for 2 years, so I don't know whether it will be possible for me to work with you. Of course, he wanted to go and meet the great man. And Einstein replied very politely, thank you for your letter. But again, he's still defending his idea that the Planck distribution is not due to photons alone, but there is some interaction. I am not in agreement with your basic principle concerning the probability of interaction and so on. However, he has published his paper. So apparently Bose had a third paper which Einstein refused to publish, but that's a different story. And meanwhile, Einstein himself, while he says I'm not in agreement with your idea, he was feverishly working on Bose's idea. So in 1924, he worked on the statistical distribution of atoms in a monatomic ideal gas, which really the only difference with what Bose's calculation is that you keep the number constant. So these are massive particles, and you get a massive boson gas. And that immediately has this phenomenon that the molecules cluster at the ground state, which is known as Bose-Einstein condensation. Now, these papers were by Einstein alone, you see. No Bose in this. But Einstein was generous enough to accept that the method he was using had been discovered by Bose, but he was not going to share this glory with some obscure person from Asia whom he had never met. It was, in fact, Paul Dirac who made Bose immortal. In 1926, he called the expressions Bose-Einstein statistics. And the other one for particles, which are restricted to only one per state, well, he called Fermi-Dirac statistics. And being very modest, he didn't call them Diracons, he called them fermions. So to match the fermions, these other things had to be bosons and not Einsteinions. So these names have stayed since. Through Einstein, Bose soon came to know the whole Berlin gang, and the very famous people, Max Planck himself, Walter Nernst, Hahn, Lisa Meitner, von Karman, Schiller, Wigner, De Bayer, Hermann Mark, with whom he actually worked, Haber of Haber's process, but everything revolved, around one great man. So he towered over all the others. And Einstein suggested to Bose that they should collaborate on two problems. Again, you see Einstein is sticking to the old. Whether their new states imply some subtle interactions between the photons themselves. And the answer is no, it does not. There is interaction between photons, but it's too weak to matter. How could the transition probabilities of spontaneous and stimulated emission be derived in new quantum mechanics? Now, this problem was much too. So the first one was not workable because there is no such interaction. The second one requires a perturbative calculation, the dipole approximation. So quantum mechanics had to develop much further before these could be solved. So not surprisingly, Bose did not make any headway in other problems. So since he couldn't solve anything, he started working in Hermann Mark's crystallography lab, where he could do the work, continue the work he had been doing with Morris de Broglie. Of course, he visited Einstein regularly and had all manner of discussions with him, but these two problems remain unfinished. So there is no paper, no Bose-Einstein paper as such. And in mid-1926, he had to come back to India. In 1926, he returned to Dhaka. Of course, he still didn't have a PhD, but he had reference letters from Einstein, Lajova, Hermann Mark. So they promptly made him professor and head of the Department of Physics at Dhaka University. After 1 year, he was also made Dean of Science. And as such, he set up laboratories in chemistry, optics, and crystallography and started publishing in these areas. In 1938, he was recalled to Calcutta University to take up the Palith professorship. He didn't take it up. Instead, Meghnad Saha took it. And then, of course, there have been many other people after that. But I'll take this opportunity to show you a picture, it's a very cherished picture of myself, of course, not just with, so this was the head of department's office in Dhaka University. You see, of course, he had another very famous physicist, Professor Ashok Sen, and this is Professor Arshad Momen of that university. But I'll show you this board. Let me blow it up. And you see here, W.A. Jenkins, 1921 to 96, and then Professor S.N. Bose, 1926 till 30th September 1945. A long period. And then, of course, other well-known people. So you see here, S.N. Bose. So it was really a privilege to see this. And now, what are the kind of work which he did there? Well, here is some work he did. You see in chemistry, electrochemistry, radioactivity. 2 works on statistics. This D2 statistics is the thing discovered by Mahalanobis, and he worked on that. Radiophysics. These are 2 papers on radiophysics. Then he comes back, studies in the Lorentz group towards more mathematical physics. This is certainly quantum mechanics, so being written as late as 1940, solutions of the Klein-Gordon, inhomogeneous Klein-Gordon equation. Again, chemistry, Dirac equations, so on. So you see that he worked on a wide range of things. Basically, he did whatever he really liked at the moment. In 1945, he accepted the Khaira professorship at Calcutta University, left Dhaka forever. By then, Hindu-Muslim riots and feeling of insecurity in East Bengal, it was soon to become East Pakistan, must have prompted this decision. For he really had come to love Dhaka. He had not planned to leave Dhaka. He sort of felt constrained that he would have to leave Dhaka. In 1947 came independence, second partition of Bengal. All these pictures, well, they only look too familiar nowadays, again, but these things happen. But actually it happened because Dirac visited Kolkata in 1957, and he was aghast to know that the great S.N. Bose was not FRS. So when Dirac, who was then the president of the Royal Society, went back and nominated him, that's how he became a fellow of the Royal Society. In 1959, he was appointed national professor for 5 years, and this position was renewed so long as he lived. Calcutta University made him emeritus professor and gave him a lab and grants to work through the Indian Association of Cultivation of Science. But by now he was 65, so aging, but he continued to train students in experimental techniques. Another interesting thing in his life was he wanted to teach science to be taught in the mother tongue. So he founded the Bongyo Bigyan Parishad in 1948. He was appointed president of the Indian Statistical Institute at age 73. He would remain president till his death. Then we come to 1974, which was Bose's 80th year, as well as the 50th year of the Bose statistics. So during this year-long celebrations were held in Kolkata and elsewhere, a long round of seminars, symposia, felicitations, and cultural programs. And characteristically, Bose himself was the most enthusiastic participant. So he felt actually vindicated. He said, "Now I feel I do not need to live any longer." He was a complete product of the Bengal Renaissance. He was a mathematician, a physicist, chemist, spectroscopist. He was a great musician. He used to play the esraj. He was a great conversationalist. Therefore, he was undeniably the founder of quantum statistics and therefore a pioneer of a great deal of modern science. And that is enough. We shouldn't ask what Bose did afterwards. Finally, that's the formula. That's what will remain when none of us are there, when Bose is completely forgotten. This formula will remain forever. Thank you. Thank you very much.